Welcome back to another video on speech processing. We will look at speech recognition. And thanks are given to Jeff Adams for some of the slides. He has started some startups, companies with speech processing, including Cobalt Speech and Language. And anyway, he's a BYU grad, by the way. So let's review real quick. Phonetics is our sounds in isolation, right? And we can represent those with IPA symbols or ARPABET symbols, right? Which we see in the CMU dictionary, pronunciation dictionary. Phonology is how sounds affect each other and how sounds are organized. And lexical representations, right? Orthography and how we need to go from orthography to some phonetic or phonemic representation. That is a representation of sounds or representation of family of sounds. We talked about file formats in audio files, right? Acoustic modeling, feature sets, creating feature sets, language modeling, that is getting n-gram models, and as well as hidden Markov models, and the fact that we can approximate what happened before by just looking at the closest thing from before. So what is speech recognition, or ASR? Well, it's automatically recognizing spoken language, right? It's known by other things, speech to text, automatic speech transcription, voice dictation. I think Google Docs, if you look under tools, it has voice typing. It's all ASR, or speech recognition. And it involves lots of related fields, digital signal processing, so as we saw, some math and engineering, deals with phonetics and acoustic and articulatory phonetics. We need some speech corpora, right? And language modeling and statistics and probabilities. And speech recognition is one of the nifty 50s of the National Science Foundation. The nifty 50, the 50s are NSF-funded inventions, innovations, and discoveries that have become commonplace in our lives, and it is one of them. I think it is 43. So there you go. It much of the research that kind of went into discovering or producing, not discovering, but producing speech recognition was funded by the National Science Foundation. It's a prior stage of many different applications, right? Speech understanding or spoken language ID, like it's identifying what language is being spoken in an audio file. Interactive dialogue systems, as we know, digital assistants and the like, as well as spoken language translation, speaking in one language, having it understand it, transcribe it, do machine translation, and then TTS it, that is text to speech it back out. All of that, right? And so speech recognition is an important step in many of these technologies. So here's a short history of some of the ASR or speech recognition. I'll use those interchangeably, by the way, speech recognition and ASR. In 1946, sound spectrogram for speech analysis was invented. And in the 50s and 60s of the 20th century, had some preliminary research. But in 1969, John R. Price gave a report to the U.S. Congress that kind of killed research in the field. Here I have a Wikipedia article talking about who this was. As an American engineer and author, he did extensive work concerning radio communication, microwave technology, computer music, psychoacoustics, and science fiction. Good. Worked at Bell Laboratories, right? Developed jointly the concept of pulse code modulation, PCM, at Bell Laboratories with his colleagues there. So anyway, he gave a report to Congress and said it's not really worth the money that we're putting into this technology. So it kind of killed it for a bit. But by the mid 70s, and this person, Charles Wayne, at the DARPA Institute, proposes competitive evaluation, that he proposes like competitions to try and build speech recognition models. And so continue down into the mid 2010s, where we start using neural network speech applications with machine learning, robust machine learning models. So here's a conceptual overview of ASR, or speech recognition, right? You have input that you convert from analog into digital format with windowing and sampling, right? and then, well, sampling. And then you analyze the signal with what we saw with windowing, and then doing that mathematical, all those different mathematical steps, taking the log, doing a MEL scale. And that comes down into the search area here. We also, before that, we have a phone model, right? We have kind of three different ways of looking at a phone, like what happens before, what happens after, and even within the same sound, we can have like a beginning, middle, and end. And that is created on training data, like a lot of language, right? And we have a compiled language model, like an Ngram model, that gives probabilities of words. Okay, so we have like probabilities of phones here and probability of words here. And those combine together to produce text, right? Actual text, which hopefully is faithful to what was actually said. Here's a bit more detail, right? We have our speech waveform here that gets windowed. We extract the features out of each of these overlapping windows. We end up with a feature vector here of numbers, right? And those come down and are used with different mathematical and machine learning technologies here to come down into the text, right? Passing through probabilities. Like, what is the probability that we get these sounds in this combination, right? Coming from phone likelihood models, like the probability of this phone versus that phone, or the probability of this phone given the previous phone. Okay. Anyway, this is kind of a quick schematic architecture of speech recognizers from a textbook. So the ASR problem linguistically, well, we receive acoustic signal and we want to extract the text, right? So we analyze waveforms, sample the signal, do windowing. We detect and segment spoken language, speech segmentation, and we associate those acoustic segments with phones where we map it, right? And then we classify phonemes and allophones, classification, and we construct higher elements of structure. So syllables and morphemes and words, right? And so it's kind of this from left to right process. We have speech, we break it down into, phonemes, which we then combine with probabilistically into words, and then we combine those words probabilistically into phrases, the language model. Right, so we have an acoustic model that tells us what phone we're listening to, and then we have a lexicon, like a grapheme to phoneme, the result of a grapheme to phoneme step, where we take the phonemes and produce orthography. We're going reverse, actually it's phoneme to grapheme this way, and then the language model tells us what words are likely coming together, going together. So kind of building small up until we have like full sentences. So there are multiple models, multiple hypotheses. You map a feature set to a phoneme. When you do that, it's not deterministic, meaning there's not like always a right way to do it. It's probabilistic or stochastic. Stochastic is a fancy word for probabilistic. And so we have a signal here on the right, and then we say these sounds could be the phoneme a or e or I. Okay, so we have some hypotheses here for this sound. And then the next level, we have, some possible words that it could be saying. It could be I, as in the thing you see with on your face, or I, the first person subject pronoun in English, right? Or ice, perhaps. And so we have like these probabilities of these words are possible, and we need these different resources: the acoustic model, the lexicon that is produced by a G2P tool, and the language model to figure out the probabilities between words. So these all go into speech recognition. I speak to my, right, is the most probable phrase given this sound, going through all these different steps. Typical ASR components, well, it's kind of what I just said: the acoustic model, lexical model, like a dictionary or a G2P, right? Something produced by a G2P, and language model, like an Ngram ARPA file model. So here I have some more information about the three kind of models that go into ASR: the acoustic model, the lexical model, and the language models. It's basically just this idea of going from a speech sound to a likely phoneme, and then a likely sequence of phonemes to a word, and then a likely sequence of words. A likely sequence of phonemes that is a word to a likely sequence of words. Just kind of building little by little, having probabilistic measures in there all the way through. Here's a review of a slide we saw in a previous lecture. Again, kind of the same idea. We have sound, we break it down with windowing down to feature vectors. And over here we have a language lexicon here, like a G to P, the grapheme to phoneme conversion. And then we go through a hidden Markov model type idea, taking each one and saying, okay, now are we still in the end? Yeah, we're still in the end. Let's go. Yeah, we're still in the end here. And then we move to the I there, 9. So that's how you train speech models. So let's review feature extraction and acoustic modeling. Describe a frame of the signal in a concise way. You summarize it with a set of acoustic features, right? And you can have deltas and higher level deltas like second derivatives. And the result is, maybe 50 to 60 features that we can reduce down to a smaller number with a linear transform. And the result is a point in an n-dimensional space that we can model, a multi-dimensional space that we can model. So for example, here is the vowel space of a male received pronunciation speaker of British English. RP meaning received pronunciation, like the BBC English. And we don't produce the same vowel exactly the same time, the same way every time. So for example, with his fleece, his production of that vowel, E, this and the vowel in fleece, is up here in this region. Again, the F2, the first F2 is format 2, F1 is format 1. F1 gives the height in the mouth in the vowel space, and F2 gives the backness in the mouth. And so the idea is that there's not just one point that we always use the same articulation of vowels, but there's a range. That's why these ellipses are like that. And you can see there's often overlap. There's not clean boundaries between these regions as well. So acoustic modeling is how do we map these different points in this feature space and map it to a given phoneme. And it's much more complicated than just identifying a given point. Like I mentioned, the boundaries are not clean. There's overlap, quite a bit of overlap. And so you might think of phonemes as kind of a path rather than a destination, and especially diphthongs. So over here on the bottom right, let me move myself off of the screen for a second. We have the path of a speaker saying I, that diphthong. I, that right there, right? This is the path in this multidimensional space that, reduced down to 2 dimensions right here, right? That this vowel or this diphthong takes. And we can capture individual components of the phoneme's pronunciation in this feature space. And being context dependent is best. As we saw earlier, phonemes are influenced by their flanking phonemes. And so having, being able to look to the left and the right of the current phoneme is important. That's what context dependent phoneme modeling is referring to. Okay. Right, the prior and following context is also important. Good, context dependent. Phoneme is best. So here's like state 1, and then we move up to this state over here. We move down here, and then finally end up right there. And I think this is need. Yeah, this is a model of need. So we can use a hidden Markov model for one diphthong, the I in the first person pronoun I or ice, right? Or the thing I see with my eye. So there are 3 substates. We can break down the phoneme into like 3 independent like substates of that one thing. We have like a beginning, middle, and end of the phoneme. So underlying each substate is a mixture of probabilistic models called a Gaussian mixture model. Don't need to stop and worry about that too much right now. And derived from the training data. We merge these different hidden Markov models together to create a huge automaton of possible sequences and subsequences, like hundreds of thousands of possibilities. And we have probabilities here on these arcs, right? As we saw earlier, all the arcs, the probabilities add up to 1. So 0.2, 0.8, that's 1, right? 0.7, 0.3, that's 1. So that we can break down even phonemes. So these are all the same phoneme. We're trying to model I with silence before it and S behind it on the right side of it. So here is a recording. Let me just play it.
I suddenly felt dizzy when I stood up.
I suddenly felt dizzy when I stood up. So each different color line is a different word in the utterance she just said. And you may recognize this pink or purple line. We just saw it 2 slides ago, or 3 slides ago. That's what this is. That's I. And then she goes to I felt. So felt takes this path. The idea here is that, excuse me, we can see the path. We can watch and model the path that each sound and phoneme takes in this feature space. Okay. So the challenge is to map these phoneme paths to words. That's the challenge. So segmentation and decoding. First step is to segment the incoming speech, continuous speech, perhaps with pauses, into actual segments, to actual phonemes and some representation of sounds, right, like an ARPA-BET or IPA. And then the next one is to decode it and try and find the best state sequence for a given observation sequence using n-gram models, as well as this Virtubi algorithm. The Virtubi is a dynamic programming algorithm for obtaining the maximum a posteriori probability estimate of the most likely sequence of hidden states called the Virtubi path. That results in a sequence of observed events, especially in the context of of Markov information sources and hidden Markov models. So this algorithm is used. There's other ones as well. But it solves both problems, segmentation and decoding. And it works best with bigram grammars. Okay. So another important step is training. There are 2 steps to building up data structure ASR needs. The training, given a phone set and a lexicon, an audio file, and phoneme level transcriptions, like transcription of audio files down to the phoneme, like this phoneme right here, this little slice of sound is this one phoneme that has to be done, has to be fed into the model to train it. You build a whole sequence of hidden Markov models for each sentence, and you compute the transitional probabilities over several iterations until convergence. And again, using some algorithm, this Baum-Welch one goes forward and backward. It makes use of the forward and backward algorithm to compute the statistics for the expectation step, again, based on hidden Markov model ideas. Okay, and the decoding, oops, let me go back, sorry. The decoding is given a set of hypotheses for phoneme or word sequences. Traverse the hidden Markov model in order to account for the best sequence of phonemes and words in the language grammar. So here's a schematic of how the search happens. Let's say we have these hypothesized sounds and these words. And so we can see here that we hear an it can be part of I or part of on. But it says, hey, this is a better probability. There's a higher number here, right, than that number there. And then we go to n, and we look at the probabilities of n for the different words. So that's just a quick little schematic from a textbook about how the Viterbi decoding search happens. Let's move on. There are other decoding algorithms. There's more advanced ones. The NBEST is kind of a modified Viterbi. Has a 2-stage model that the first pass is with an efficient rough lookup, like with bigrams. The second pass is more sophisticated, like with trigrams. And there's another one called an A-star or stack decoder. It has this priority queue that keeps track of the different priorities or different probabilities as it's going through. So we talk about a noisy channel model in which you have a source sentence on the left-hand side of the bottom of the screen, and it goes through some noisy channel like a microphone or a telephone or radio waves or a file upload or file compression. and you end up with a noisy sentence, and then you have a decoder that tries to guess at the original sentence. You might even think of human language translation as this type of model. We have like the original source language, and we go through a translation process, which is like the noisy channel. We try and create a translation in the target language that gets at the same meaning as in the source. This is widely used in language processing and in other fields as well. Okay. So to summarize, there are kind of five basic pieces to ASR. There's a feature extraction, like with the MFCs, getting a feature set, a vector of numbers. We have an acoustic model. That is, what's the probability of this sound, this sound representing this phoneme. And then we have a lexicon or a pronunciation model, like a G2P model, right, that maps phones or sounds to words. Then we have a language model that is looking at the probability of this word given the previous word. And then we have a decoder, that Viterbi algorithm or one like it, that combines all of these to get word sequences from speech. That's a kind of quick, high-level rundown of what happens with ASR. And also, as you would imagine, they gauge or judge how accurate ASR systems are with a word error rate or an accuracy rate. And it's simply the number of substitutions or insertions or deletions that you have to put in, divided by the total number of words in the test set, and pushing that to a percentage gives you a word error rate, and the inverse is an accuracy rate. And so that's how they measure how well the ASR system does. And there are competitive evaluations. So let's take a look at this. The National Institute of Standards and Technologies, NIST for short, has competitions. Here's one, the Open ASR Challenge from NIST. The goal of the Open ASR Challenge is to assess the state of the art of ASR technologies for low resource languages. Cool. The Open ASR Challenge is an open challenge created out of the Intelligence Advanced Research Projects Activity Material Machine Translation for English Retrieval of Information. Okay, cool. Program that encompasses more tasks, including cross-language information retrieval, domain-specific, etc. Anyway, there's competitions that they sponsor and have sponsored over the years, over the decades. Just language recognition, right? They have that one. They have other things, speaker recognition, like when you diarize or source separate two speakers in the same recording from each other, broadcast news recognition, and others. Easy versus hard. Well, ASR is not a solved problem. All applications have some errors, and the key is to design a system that does some things well, right? And so trying to figure out what the application that the ASR system will be used for, and that would determine what training materials you use to create the ASR system, right? So it's easier if you have a small vocabulary in a quiet environment with, a high quality mic and very deliberate, careful speech, and you have one speaker, right? It's much harder if you have unlimited vocabulary with a noisy environment and a distant mic, right? Spontaneous speech rather than careful speech. There are other factors that go into making it harder, right? Speaker idiolex, that is the speech of the specific individuals. Psychological condition or emotion, right, can have an effect on the accuracy of ASR systems, right? Semantic and syntactic ambiguity can work into it as well as other things. Here are many links to useful resources around ASR technologies. Google Scholar, right? I'm sure you're very aware of Google Scholar. If you just type in speech recognition, in the profiles, you can see some of the researchers in speech recognition. This is the ISCA, the International Speech Communication Association, and the Interspeech Conference that deals with speech technologies. The Association for Computational Linguistics Anthology, right, has a bunch of events and links to their websites. The archive has several subtopics, for example, acoustics and speech. And you can see recent submissions to this sub part of archive. Cool. Speech enhancement for virtual meetings on cellular networks. There's a paper about that. And there's another one here, computation and language. Wikipedia, if you just look at the Wikipedia article about speech recognition, you can, read what they have here and also look at the references. Obviously, this is the case with any Wikipedia article. Looking at the references and where they get the information can be useful. This is the Association for the Advancement of Artificial Intelligence. I'll have to get that link working again. Anyway, all sorts of stuff here. The Linguistic Data Consortium, which we are familiar with, and the European Language Resources Association is kind of like the European version of the LDC, and obviously GitHub. So a lot of resources out there on ASR technologies. ASR toolkits and levels of support. Some are basic and just an application programming interface to some online ASR system, like with Google, for example. And that will be one of the tasks, is to just use something like that. So you have no access to the source code, nor model training. You're just simply using what they've created. Many are commercial and require subscription, not all, but they're pretty simple to use. Ones that take more programming access and you have a full access to source code are complex, and you need good programming skills to integrate new things and create new models. But you do have the ability to train new models, which is, like I said, can be useful if some ASR system is not working well for what you're trying to do. You can create your own model if you have training data, or you can get training data to do so. Okay, there's a lot of third-party contributors as well. Here's some of the commercial systems and API and cloud services. Amazon Web Services, right, has Amazon Transcribe there, automatically converts speech to text. That's ASR. Google has one, speech to text right there. Try it for free, right? You get, a free tier there for transcription. Nuance. Jeff Adams, who I mentioned earlier in this video, worked for Nuance. It is a big player in ASR systems, and there are others as well. And some open source systems that are available. SpeechBrain is a collaborative effort, kind of hosted or coordinated at McGill University in Canada, and it is an all-in-one open source conversational AI toolkit based on PyTorch. It can do all sorts of really cool things, and one of your tasks will be to use this. There's speech recognition there. Okay, Whisper from OpenAI, the company OpenAI, right? The chat GPT company OpenAI has released a really big ASR system called Whisper. Very good. I've used it successfully in Spanish and English, L2 Spanish, and some distant microphone English. It worked pretty well. So that's really cool. Nemo. This system is created by NVIDIA. Not sure how to pronounce that name. I recognize the name, but I'm not sure how to pronounce it. I'm not sure if I've ever heard it pronounced. They have a toolkit where you can create your own ASR systems or TTS using large language models and natural language processing tasks, right? So that is available. They have just pre-trained models you can just download and use, or they have the ability it has the ability to train up a new ASR model. Anyway, others, I'll let you click on these other ones down here if you like. So yeah, the three ASR labs, number one is how to use APIs. Number two is write some code to call an ASR engine, source distribution. And then number three is to train your own system, if you can. You may need to cut down the amount of training data so it actually finishes in a reasonable amount of time. Using SpeechBrain or Nemo or something other that you find, some other system that you would like to try that you find to create your own ASR model. Okay, so that brings us to a conclusion of this video. So we'll see you next time.